All right, we're here for the sixth and final session of Special Relativity and Linear Algebra. Ajeet, you can go ahead and get started.
Great, thanks. All right, hello, my loyal audience. So I left a link in the chat. It is the notes for the seminar so far. They never seem to end. I must have put 100 hours into this thing, and it's I'm still filling in pieces of it, but it's pretty comprehensive at this point. And what I wanted to do today, A, is we have some loose ends to tie up from previous lessons, but B is I wanted to really drive home the global picture that I wanted here. Excuse me. I think my viewpoint on special relativity can be summed up in that I would like to look along the causality lines and think of things as causal diamonds. We can do Lorentz transformations along those lines. They're the eigenvectors of the Lorentz transformation. So everything is just like a stretch or a squeeze in that perspective, as opposed to the perspective that physicists like to take, which is the normal like kind of x-axis, t-axis, horizontal, vertical perspective, which feels natural because it's space and time, but feels very unnatural in the weird effects that ensue. So we started off by trying to break the idea of the horizontal and the vertical by arguing away simultaneity and things like that. And then we constructed up this this causality grid arguments along the lines like y equals 1 and y equals x and y equals negative x. So right, so I wanted to tie up some loose ends and then discuss this causality grid argument against the space and time argument. So Einstein has a way of thinking about special relativity called Einstein Synchronization, which was kind of like this desperate attempt to salvage simultaneity. And I would like to compare that against the causality grid and really try to argue away this clinging to very independent notions of space and time. Okay, so right, so let's jump into Einstein synchronization. We'll start there, and then I can kind of retell the story from there. So let me share a screen. Right, so the first link in the chat is the notes, almost finished, and then the second link in the chat is the link to the Mathematica package. Okay, so right, let's just share my entire screen. Okay, great. So you guys should be able to see that now. All right, so this is on my website. So I've rearranged some things. So we start off with just arguing about space-time. You know, space is a silly concept. Time isn't what you think it is. And then causality and simultaneity are trying to create this causal grid notion. Causal diamonds is going into how to interpret that causal grid. The space-time invariant is where the linear algebra starts to really take shape. So we've talked about this before, but a quick recap on what the space-time invariant is it's a metric on the space, or a two form if you want. It's actually a pseudo metric for mathematicians. And the idea is that it's like this distance function that is invariant of reference frame. The normal Euclidean distance function changes based off how fast you're going, which doesn't sound like a very good way to do physics. But the space-time invariance is, as the name suggests, invariant of reference frame. That's like the one true thing in special relativity we can rely on. It's like the speed of light and the space-time invariance. So that's a perspective that I really like to focus on in this text, because space and time are pretty arbitrary in some ways of looking at it. On which note, we're going to start talking about length contraction today, like very rigorously. I've mentioned before, but I can finally show you pictorially where physicists are getting caught on something. Relativistic paradoxes, we've talked about some of these before, but we have some details to fill in. I have some new effects to show you. One of them is called relativistic beaming. And then if we have time, I might say something about relativistic motion. And unfortunately, my virtual reality special relativity is not in a form I would like to share with you yet. But yeah, exasperated. But yeah, you can be assured that it'll be on my website eventually. I put way too much work into this to stop now. So yeah, my goal is to wrap everything up by the end of the semester so I can focus on other things in the summer. But we'll see. But all right, so yeah, let's get to synchronization. Okay. So Einstein really wanted this idea of simultaneity to work. So he came up with this, in my opinion, quite barbaric way to salvage simultaneity. So yeah, this is called the Einstein Poincare synchronization. The idea is, remember, the horizontal axis is space and the vertical axis is time. So the clocks you see here are all like just traveling at rest through time. They're at stationary in space and they're traveling through time vertically. So the idea is we start with one clock here and we send out a light signal in both directions. And then the light signal bounces off these clocks, which are also like reflective surfaces, and they come back to the original clock. And you take like the average of the time here and the time here to sync up these clocks. The idea is that after letting light bounce between them, you can reverse engineer what these clocks should be set to so they can all be set to the same thing. Okay, all set to the same thing. What does that even mean? We've already argued away that doing horizontal lines on a space-time diagram is a nonsense thing to do. But if you do it inside of this like causal diamond thing here, then we can salvage a horizontal line. So if I'm just standing around and I say, oh, to my left, to my right, this is a simultaneous slice of reality, it's a nonsense statement because, as we mentioned before, our space-time ruler would have to be tilted horizontal in space and time. It'd be a measurement that takes 0 time to make. It's way faster than the speed of light, infinite speed. It doesn't exist. But if I set some things up ahead of time, I give myself some time for these clocks to get synchronized, then I can start to talk about horizontal lines. But the reason that I didn't just show you this grid of synchronized clocks here, and I showed you the beginning of it here, is because I wanted to show that in order to talk about these simultaneity slices, you need to first do a causal diamond type thing. You're still limited by a light cone, is the idea. So you have like a causality cone or a light cone here to set up your synchronization. And then within that cone, you can have this grid of synchronized clocks. So now that you've already synchronized your clocks, you can see that along, oh, sorry, the red lines are the outgoing pulse and the pink lines are the reflected pulse. But you can see you can have horizontal lines here of clocks that are all set to the same time. And that gives you a notion of simultaneity. Right, so then this isn't a universal notion. And if you wanted, like in particular, if you wanted to set up a synchronization of clocks across the entire observable universe, I mean, it'd take you an infinite amount of time because you just can only creep out at the speed of causality or the speed of light to even set up these synchronized clocks. So the right, so then to use our causal diamond explanation from last time, a quick reminder on that. The idea is I'm on Earth and you're floating through space. We both have a little laboratory and we compare ahead of time to make sure our laboratories are the same size. And then in my laboratory and your laboratory, we're both trying to come up with some measure of length and some measure of time. But all we have is the speed of light and like some mirrors. So we shoot off this beam of light, it bounces off 2 walls, and then it meets back in the middle. So what we can do is like we can find the middle of our box because we can make sure the light rays get back to us at the same time. We can find the middle of the box, and we can also kind of arbitrarily then define a length unit and a time unit, but we don't have 2 pieces of information to do that. We just have one standard, and that's the speed of light. The speed of light, or the speed of causality, is a relationship between space and time, and we have to use that to define a meter stick and to define a clock. So we have 1 unit to define 2 physical units. So then one constant to define 2 physical units. Really, we're just dealing with 1 piece of information. But essentially what Einstein is doing here, he's saying, all right, everyone in your own little boxes flying through space, you can set up these clock diamonds, like these causal diamonds, like, you know, these little experiments. And what I want you to do is just do like a really big experiment, you know, like really set the bounds here, like create some arbitrary units of length and time. And, you know, once you've got the landscape of your box, you have these arbitrary units set up, then go ahead and start placing some clocks down and synchronizing them. So through space and time, you're in a giant causal diamond. And inside that giant causal diamond, you can set up a rectangular synchronization box, okay? So the reason that diamonds are fundamental and you can always get away with doing that, or you can always do those, you know, with no argument, is that this causality grid, this background speed of light or speed of causality being constant, is something you can rely on. You can always travel along these light rays. It's easy to do. Send a light pulse that way and a light pulse that way, or a gravitational wave or whatever, something moving at the speed of causality. And that's a reliable way to set up a grid on the world. It just happens to be diagonal through space and time. The tricky thing is trying to get a grid that's horizontal through space and vertical through time. You can't do it like a priori. You can only do it after you've already set up some sort of causality grid ahead of time. Okay, so boxes are not the natural way to think about space-time. Diamonds are, but boxes are natural to our dumb Newtonian intuition that wants things to be independent between space and time. So to salvage our Newtonian intuition, you can set up this kind of box structure inside of the diamond structure. Okay. Any questions on that? Okay, so special relativity textbook. Well, okay, there aren't any special relativity textbooks. That's part of the reason that the seminar exists, is because I'm frustrated that I can't find like a coherent text on special relativity itself. But the modern physics textbooks or general relativity textbooks will often start off with saying that special relativity relies on a grid of synchronized clocks. So just like in all three spatial dimensions and the time dimension, this like grid of evenly spaced, so clocks separated by meter sticks. These little blue lines are like meter sticks, is how they like to say it in the textbooks. So an infinite grid of clocks separated by meter sticks that are all synchronized. So they say, oh yeah, we rely on this background grid so that we can even talk about space and time. And that always felt like a ridiculous starting point to me. Like, how can you posit that there's a grid of clocks and meter sticks over all of space and time and then go from there? It's a ridiculous starting point. If we actually look at the synchronization process, we see that it is inside of a causality cone. To set up this, you cannot possibly set up that grid any faster than a causality cone. And I think that makes it a little more palatable, because you know that someone did a lot of work on a causality grid background to set up your nice horizontal and vertical grid of clocks and meter sticks, which makes life easy for the physicists because they can define things like, oh, this object is this long in our synchronized clock grid, and not have to use space-time rulers. They can use like literal rulers inside of a causality cone. So that makes it easy for them, but I also think it's a giant downfall because they end up defining silly things like length contraction. Okay, so let's get to length contraction. Here's Einstein's picture of length contraction. So there's right. Some people like to argue that length contraction is not like a real effect, and Einstein rebutted by saying it's as real as any other physical thing you can measure. The whole argument is silly. The thing I started off this entire text with was a quote by Descartes. Imagination is more of a hindrance than a help in metaphysical speculations. Use imagination for math to create cool constructs, but when it comes to physics, just try to stay literal. Just try to remember that all the physics we do is just an attempt to apply math to reality. All we're ever really doing is math. All we're really doing is comparing a measurement, which is something done by a human, against a mathematical theorem, which is something made by a human. If it reflects reality, that'd be great. But we're always just kind of doing math. And it would do us good to remember that, so we don't come up with someone like reify these kind of like fanciful statements about reality. So physicists like to say that when something's going fast, space contracts. It gets like space itself not squishes, because there's no tension forces or anything. Like the object doesn't physically get compressed, and the object doesn't know it's being contracted either. The object doesn't feel like it's getting contracted. If you are going fast, you don't feel like, you don't see your fingers get closer together or anything like that. But in a measurement of that object would see it smaller. So they say that space itself contracts, but this is very, very misleading. Okay, so this is something I reconstructed as a sketch that Einstein made about how length contraction would work. What's going on here is the green is a rest frame x-axis and a rest frame t-axis, so space and time. The red is a moving frame. The x prime prime is some moving frame, and t prime prime is the corresponding time axis, and then the blue one, x prime and t prime, are moving the other direction but the same speed. So we have is a green rest frame that we're going to do a measurement in, and then we have a red frame that's moving at a certain speed in one direction. I said it's a 0.5 c, and then the blue frame is moving at 0.5 c in the other direction. Okay, the tick marks on these axes are spaced out as they would be observed by the moving observer. So there's a couple ways we can think about this. You can pick your favorite explanation. The worst explanation is that the tick marks are already experiencing the length contraction, but I don't like that explanation at all. It doesn't give you any insight into what's going on. Another explanation, a better one, would be that the causal diamonds are stretched out. So when they do experiments in their relatively moving reference frame, that's just how the light bounces off of their walls. Like for them, they feel like the light bounces off the walls the same way that we do when they do their little clock experiments. But from our perspective, we see them like their light rays like running into their walls at different times than they expect. The idea is that we're doing the same experiment. It's just that their experiment is in a moving box. So it's just their ticks when they count their clock in their little the little box. It looks slanted through space and time to us because they're moving at a slanted pace through space and time, right? Okay. Another explanation is you hit it with a Lorentz boost. We argued why the Lorentz boost takes the form it does. And then we even showed it in the causality basis, which was like a diagonal matrix, which is really nice. You can just boost this axis into this axis, and that's how tick marks are labeled. We can even do one more explanation if you like this one better. The space-time metric is the invariant. So space-time metric, right? So it's a pseudometric, really. But the idea is that it's this, it's like this two form, and so when you have a metric or even a pseudometric, you can create a quadratic form out of it, which just means you feed the same vector into the left side and the right side, and all of a sudden you get a quadratic function. And then the level sets of that quadratic function are going to be the curves along which space-time events are like travel, so to speak, as you boost. So like the analogy is if you had a very, very simple quadratic form, just x squared plus y squared or x squared plus t squared, that's just like your Euclidean one. And any level set is going to be a circle. So that's like if your invariance is about rotation, if something in physics has rotational symmetry, then you could either think of it as, oh, well, you have this equivalence class around the circle, or you could say, oh, well, really parameterize it by the Euclidean norm. And then that naturally leads to the circle argument. That's all trigonometry, right? Just that circles and the Pythagorean theorem describe the same thing. Here we have like a hyperbolic version of it. So the space-time metric is x squared minus t squared. So the level sets of that are actually hyperbolas. So then I slanted these lines so they'd be tangent to the hyperbola that they live on. So I know it's hard to construct a hyperbola with 3 points in your mind, but there are hyperbolas that come through here. And you can just imagine all the points traveling along these hyperbolas. Okay, those are a bunch of different ways to justify why the tick marks are where they are. In particular, 3 ways to do it without saying that the axes are already length contracted or space contracted or time dilated. Doing that would totally beg the question here. So, okay, so let's see space contraction now. So I worked out a calculation that I still need to put in the notes. It took forever, but it turns out that the length contraction that physicists are talking about, what they mean by that is they're saying if you're in this green rest frame and you have some observer that's, or you have some object that's moving in either direction here, like the blue or the red. And so in their reference frame, their proper length here, 1, 2, 3, 4, 5, proper length as in the length of the object in their reference frame. I mean, that's the invariant way to talk about length. If length gets contracted in different reference frames, then the invariant way to talk about it is how long is it from the reference frame attached to the moving object, the reference frame in which the object appears stationary. Okay, so it's 5 in this and it's 5 in this. They say, so you see the object passing through your stationary reference frame, and if you take a simultaneity slice, which should already be a red flag because we hate simultaneity, but you take this horizontal line here, for simultaneity, it will be less length units than the proper length measured in the moving frame. So we see here it's 5 units, and this red one is 5 units in its own reference frame, and this blue moving one is 5 units in its reference frame. But in the green reference frame, both of them are the same length, but less than 5 in the rest frame units. So this shows 2 things. One thing it shows is, the relevant, something cool that it shows is that this effect is invariant of which direction it's moving. Okay, but I think the enlightening thing is that it shows that you're taking a really arbitrary slice of the object. So like an object is smeared through space and time. Like to say, even say that an object exists is to say that some, an object exists at multiple points in space for multiple points in time. To do that is a two-dimensional thing. It's a space-time thing. Physicists try to act like saying an object exists is like a space thing. Oh, this object exists here. But I mean, it has to exist in multiple places in space and multiple places in time. It's always this world block that moves through space and time continuously, right? The thing is that block gets slanted if it's moving at all. If it's moving even at 1 mile per hour, you have to do a little Lorentz boost to even look at it properly on your diagram, and that tilts it through space and time, as we talked about before. But then the physicists will keep measuring it just as a horizontal cut through space and time as it looks to them, as if you can have this notion of simultaneity. And that's just misleading because you're just only taking a small slice of it. So I worked out the calculation. This length here is indeed the proper length times divided by the Lorentz factor, which I, for some reason, haven't found. Obviously, someone's derived it. I mean, that's how they even get it. But I haven't seen someone draw this picture and admit that physicists are taking this weird horizontal slice, and that's what they're saying is length contracted. I think it just totally undermines the idea of length contraction. For one, if you take this horizontal slice and you move it up and down, the whole notion breaks down at the edges of the object. Like down here, where the object kind of pops into existence, you can't even talk about its length anymore. This reference frame never sees it doesn't see the object fade into existence. It just says, oh, I'll start measuring the object now, and then I'll stop measuring the object here. But then this horizontal slice is like, oh, well, down here, the object only exists, only the right side of the object exists over here, and the left side doesn't exist anymore. Like, what are you talking about? It's the horizontal slice is, I think in this picture, pretty clearly not the right way to talk about an object that's moving through space and time and anything other than zero velocity. Okay. How do we feel? Does length contraction feel silly now? I hope it does. All right, cool. Yeah, I guess this whole thing is I'm telling mathematicians new physics that they haven't heard before, and then telling them that the way physicists teach it is stupid. So maybe the whole thing feels silly too. But all right. So great. So there's synchronization and there's length contraction. Let's go back to synchronization because we have some more things to nail down about simultaneity. Okay. Often the way that special relativity and general relativity are approached is that they like to say space-time is a four-dimensional manifold, and you you foliate it through time. So you take these three manifold slices. So these three-dimensional slices that you call a space slice at 1 unit of time, and you stack them. So in the one-dimensional example, it would be like these horizontal slices or just some curve slices that you stack up to, I guess a foliation is just straight lines, but it can be any kind of line as long as they stack together. So you cut space-time into a bunch of one-dimensional segments, and then you can get a notion of time by just like cutting, perpendicular through all of those segments. So in particular, the work I do at NASA, we simulate general relativistic spacetimes around black holes by doing this technique. We say, oh, this is one freeze frame. This is a three-dimensional image of the world at this instant in time. And then this is a three-dimensional vision of the world at this instant in time. And you like step through time like that. But it's like totally arbitrary. We could have picked like way different space-time slices is the thing. The choice of space-time slice is completely arbitrary in the same way that a notion of simultaneity is a totally made up construct. If you do Einstein's very aggressive synchronization, yeah, you can get synchronized clocks in a line, but that doesn't say anything fundamental about nature. Okay, so physicists like to do these space-time slices, but it's merely for convenience. And in fact, I think the mathematical way to say it would be is that you're exploiting an invariance. There's no physical notion of simultaneity, so we're free to make it up, right? This is optimistic nihilism. Simultaneity doesn't exist. So that means we can make whatever we want of it. We can just define simultaneity. So we define these simultaneity slices, and that's the foliation model of special relativity or general relativity. And it takes a similar approach as this Einstein synchronization. We just kind of make up the notion of simultaneity. Okay, cool. Length contraction, foliations, synchronizations, and boxes and diamonds, right? So I kind of talked about this, but let me drive home the point about boxes and diamonds. Any diamond can be like circumscribed, so to speak, with a box, and inscribed with a box, like a midpoint polygon kind of thing, and vice versa. So if you ever draw, so the way you would like to think of an object in space-time, or at least, it seems like physicists like to think of an object, is it's like horizontal in space, right? Like it exists at multiple points in space in the same instant, and then it exists for a certain amount of time. So it's like this box with right angles everywhere. It's the bottom of it is flush with the x-axis, and the vertical component goes up with the vertical axis. But to do that, to declare that, you'd have to be inside of a causal diamond. That's okay, because you can imagine a diamond around, and so imagine any rectangle, and then you can imagine a diamond around it. Just make the vertices up at the midpoints of actually not even the midpoints. Yeah, just imagine a rotated quadrilateral around it. So you can always make a causal diamond around it, which means in that way we can salvage these kind of rectangular these objects that are rectangles in space-time, as long as you admit that you need a causal diamond around it to even set that up. Which is exactly what Einstein synchronization does here. It says, oh, well, you don't look behind the curtain about all this causal diamond setup that we had to do. This very aggressive setup. Just look over here. Look, see, we have a grid of clocks. Awesome. But yeah, okay. So and then vice versa. If you want to go back to being a physicist, then you can take all of our causal diamonds and you can put inside of them little object boxes. You can say, okay, now we can talk about object boxes. So you've been having fun with your causality grid, but let me just put little boxes inside of it, and now we can talk about physics like Newton did again. That's like this duality of like the box viewpoint and the causal diamond viewpoint. But I would like to argue that the causal diamond viewpoint is more fundamental. You can any box you need to surround in a causal diamond to make physical sense. But if you just have a causal diamond approach, you don't have to surround it in a box or put a box in it. It can stand alone, and you can describe reality like that. To undergraduates, maybe they're fine brushing past the causal diamond thing because boxes are very Newtonian, and again, they only ever spend like a third or a half a semester on special relativity because it never gets its own class or its own textbook. And maybe that's why they don't have time to go into causal diamonds. I don't know, but yeah, I would like to insist on the causality grid, because I mean that's Einstein's postulate anyway, that the speed of light is invariant. Okay. Which is like the diagonals. Okay, exhale. Yeah. So right. This is what okay, this is the biggest update to this text so far, or in the last week or 2 weeks. Causality clocks and timeless particles. Okay, I've mentioned before that photons move at the speed of causality and that they don't experience time. And that any matter is going to need to be moving at less than the speed of causality to construct any sort of clock. And in this section, I really work out exactly why that is. So, all right, let's think about our experiment where we're setting up these causal diamonds very carefully. What we're doing is we say, all right, I'm in a box. I don't know what's going on. All I have is light and some mirrors. So I'm gonna send off a light pulse in both directions and at these mirrors and wait for it to come back to me. The light pulses come back at different times, so I adjust a little bit until they come back at the same time. Now I'm in the middle of my box. I'm in the middle of my causal diamond. I don't have an objective notion of length. I don't have an objective notion of time. But what I can do is I can just kind of create like arbitrary units for space and time, like a meter and a second. But all I know for sure is the relationship between those things. All I really know for sure are the slants, like the slope of the diamond, the causal diamond I'm living in through space and time. Because I know the speed of light or the speed of causality is always constant. That's the only thing I know for sure. Okay, I set up these little causal diamonds. But there's an assumption in there. The assumption was that I have matter for the mirrors that isn't moving at the speed of causality. If the mirrors were also moving at the speed of light, then light would never be able to catch it. They never be able to bounce off Like imagine just 3 photons flying through space. That's not a clock because the photon can't bounce, the middle photon can't bounce between the other 2. Nothing ever happens. Those 3 photons will just float through space forever, right? Like the distance between them might change, but it's not something you could ever measure because nothing happens. There's no measurement that happens. There's no collision. There's nothing. Nothing happens. And this is the fundamental property here. So here's what's going on, right? All matter is made of little things, and little things all obey these causality laws. All like tiny microscopic physical properties are being undertaken at the speed of causality. But somehow on a macroscopic scale, we see things unfolding at less than the speed of causality. We can make things like clocks. Einstein had this thought experiment called the light clock, where you just have 2 mirrors and a photon bouncing between the 2 mirrors, and that's a clock. He argued that's the simplest clock you could ever make. I prefer the argument that any clock you could ever make is made of physical matter, and fundamentally, if you zoom in really far, it's just doing like causality speed things bouncing off of things. Everything is a light clock. It has to be, because those are the fundamental players, right? But so the simplest version of this would just be 2 mirrors and a photon. Photon bounces between 2 mirrors, and now we have a notion of something happening. We can count something, 1, 2, 3, 4. Okay, so we have these little light clocks, these little causality clocks that keep time. But it's strange because everything is made of little causality speed things. But if we do this in the right way, we can have things that actually keep time. There's something that actually unfolds. And this is a really subtle and important point. And my viewpoint is that it's very anthropic. It's a very human thing. So I think it's all just like photons and other causality speed things bouncing around. But as humans, we label things. We label clusters of these photons and other objects. We label clusters of them. And then we say, hey, this is a cluster of things. And then within that cluster, we overlook most of what's going on inside of it, but we pay attention to some of the behavior of it. And then that is what gives us a notion of like change or objects existing, space and time and all of that. It's all just emergent phenomena from the way we label things. Okay, that was a little nebulous, but maybe it'll be a little more clear as we dive into this. So what happens if we try to boost something to the speed of causality? So we boost it to the highest, to the speed, we boost it to the speed limit. So the thing is that there's a speed limit, but there's not a kinetic energy limit. Kinetic energy, you might have learned in high school or something, you measure it 1/2 mv squared, where m is mass and v is velocity. That's the classical way to measure kinetic energy. And it's a measure of how fast a piece of matter is moving. So even though there's a speed limit to the universe, that's already a misleading statement because there's not a kinetic energy limit to the universe. You can accelerate something to have arbitrary kinetic energy. The kinetic energy can go to infinity. It just bunches up at this speed limit. So there's actually another measurement for speed. It's called rapidity. And what it is really, it's just if you parameterize the hyperbola as you boost a particle and it moves along one of these hyperbola. If you just parameterize that the hyperbola with some parameter, and then you move along and you just follow that parameter, that's basically the rapidity. It's like arc hyperbolic, like inverse hyperbolic tangent or something like that. And it just follows the hyperbola. And this notion of rapidity is a cooler measurement than velocity in that it doesn't bunch up at the speed of light. It can be arbitrarily big. I mean, like, what is the point of saying that there's a speed limit to the universe and speed increases in this really like weird way, like asymptotically approaching the speed of light, instead of just saying like, okay, yeah, like that way of measuring things is silly. We have a better way of measuring it that is reflective of what's going on, that does move not proportionally to kinetic energy, but topologically the same. Like it grows unboundedly. So yeah, okay, that's just another way of thinking about it. But so anyway, as we take this this boost towards the speed of light, we have to do a limit. If you do it with rapidity, the limit will look the same. So first, we're going to do it in the physicist basis, the space and time basis. So we take the limit as the boost velocity goes to 1 of this whole Lorentz transformation so this is Lorentz transformation of some space-time point xt. We take the limit as velocity goes to 1 from the left because from the right doesn't even make any sense. Like you can't, like you start faster than the speed of light and then you come down to 1. That's just like not physical. So we start from 0 and we move up towards 1. So from the left. Okay. And what happens is we get this super strange quantity. This equal sign is obviously like a quotes around that. I mean, you guys are mathematicians, you know that taking a limit, like saying it equals something is a dangerous thing to do, especially when you get like infinities and indeterminate forms and stuff. So we get x minus t times this vector infinity, negative infinity. So an infinite Lorentz transformation would kind of banish any space-time points off to some corner of space-time, some infinitely far away corner of space-time. That's a really weird thing to think about. The first way to become comfortable with that is to realize that this infinite boost is not actually physical. You can't actually accelerate anything to the speed of light. You can accelerate it arbitrarily fast, but you can't accelerate to the speed of light. No one's ever done it. It's not possible. It's like an infinite amount of energy because the kinetic energy is unbounded. There's a finite amount of energy in the universe, or at least in the observable universe. So we can't physically do this, and maybe that's reflected by these infinities here. So if you could, you would have to banish the point infinitely far away from where you started. So maybe another way of saying that is if you wanted to accelerate a piece of matter to the speed of light, you'd end up kicking it off to the end of time and the edge of space, the edge of infinite space. It doesn't even make any sense. Something that makes a little more sense is to put some deltas in here. So we imagine the distance between 2 points in space and time, 2 events rather, in space and time. They're separated by delta x and they're separated by delta t. And then we boost the whole system to the speed of light and see what happens to the separation. And we see to end up infinitely separate, infinitely far apart in space and infinitely far apart in time. So if you take some matter and you accelerate to the speed of light, it blows up. Okay. There's some subtlety in how it blows up though, which we will reveal by looking at the causality basis. So in the causality basis, we're going to use U to know. So, okay, instead of locating a point in 2-dimensional space-time by an x coordinate and a t coordinate, we're going to identify it by a U coordinate, which is along one of the forwards moving causality lines, and a D coordinate, which is moving along the other causality lines. So linear algebra is just, instead of using the x and y axes as the basis, you're just going to use basis vectors 1, 1, and 1, -1. Those are your new basis vectors. In that form, the Lorentz transformation, or the causality boost, however you want to call it, is diagonal, which is great. We derived this earlier. And in the limit, as v goes to 1 from the left, we get infinity for the, so assuming we're boosting in the u direction, or sorry, in the forwards direction, we get infinity for the u coordinate and 0 for the d coordinate. So I have a picture of this, or pictures of this. So this is what happens to our causality grid. Okay, first note is we're inside of a causality cone, so that we actually have Einstein synchronization looking like a grid. We're humoring Einstein. Okay, so let's start boosting this thing, like boosting it to oblivion. So v is equal to 0, it's nice and orthogonal. Great. V is equal to 0.5, it starts getting pretty slanted. If we try to look for where the clocks of the same time are, we have to follow these diagonal lines. This is simultaneity now along these diagonals. Okay. If we boost to 0.8 the speed of light, it's getting pretty dramatic. You can see the ends of actually where I even made this grid. Here the grid goes off screen, but here it's come in. I can only simulate it so far. I mean, I could simulate it farther, but this kind of shows the point that it's collapsing down. It's still infinite. It only actually collapses down to a line in the limits, but we're taking the limit, so that's how I wanted to depict it. Anyway, 0.9, we're getting really squished. 0.99, it's getting pretty linear. 0.999, it's almost a line. In the limit, this will become one line. So what happens is so you can notice these clocks are getting farther apart. It stretches these clocks infinitely far apart along this causality line and squishes them infinitely close together along this causality line. So intuitively, what's happening is if you take a piece of matter, which is a bunch of individual little particles, and you accelerate it to the speed of light, or the speed of causality, in the direction that you're accelerating it to, or even if you're just accelerating the reference frame. So maybe you're accelerating as you're looking at it. You know, the boost, everything's relative. You could boost it or boost you, it's the same thing. So then what happens is it's going to cease to exist as an object in the way that we know it. So what do I mean by that? I mean that to even call an object a thing is you have to have a clock inside of it. You have to have like this causal diamond going on somewhere inside of it or outside of it. Some way to even talk about its length, to do measurements on it. But as you go towards the speed of light, in that direction that it's moving, it's going to stretch out, and in the other direction, it's just going to compress down into nothingness. This is how a photon sees the world. This is why you can't make a clock out of just photons, or out of just just photons moving in the same direction. No, out of photons in general. What am I trying to say here? So if you have a photon flying through space, or even just a cluster of photons flying through space, they don't have any D component. Like in our new basis, they don't have any component in the other direction at all. They have no way of making causal diamonds. They only know one dimension. That dimension is tilted through space and time, but it's only one dimension. That's not enough to create a basis of space-time. And we can see that like analytically here is if one of these dimensions goes to 0, then all of a sudden the limiting Lorentz transformation is a rank 1 transformation. It's not invertible, it's degenerate, it collapses down a whole dimension. This is the dimension that collapses down along this diagonal. Without any space and time between, we lose the notion of measurement entirely. And this is exactly how a photon sees the world. So a photon obviously doesn't think, it's not a brain, it's not a human or a computer or anything like that. So we have to, anthropomorphize it to say something like its lifetime or anything like that. But the point is that a photon doesn't experience time at all. Like quite literally, nothing happens to it over its entire life. It's completely structureless. It's just a ray through all of space and time. Well, not all of space and time, but through a one dimension of space and time, one line. And it doesn't tick, it doesn't age. Its past, present, and future are all one instant in time. And space for it is so contracted that all it can see is itself. It can't see anything else. It doesn't interact with anything. So space contracts down to nothing, and time contracts down to nothing, and space stretches out so far that it's the only thing that exists. You can kind of explain the time and the space effects both directions. You could say space crushes down or space expands, or time crushes down or time expands, depending on whether you're explaining from the photon's point of view or another observer's point of view. Relativity. Okay. Okay. So photons are completely structureless, but through some miracle, these structureless photons that and other causality speed things that make up all matter let us define some sort of notion of length and time. But we can only do that inside of these causality clocks. We leverage these photons, we leverage the lack of structure of these photons, right? Their consistency, that they always move at the same speed, so that we may garner some sort of measure of length and time. So we can create these clocks against the background of structureless things, which I interpret to be very human. Like there has to be a human that sits down, or some conscious creature that sits down and says, this bundle of things is what I would like to look at. And I'm guessing that some smarter being, so if we live in a simulation, then the simulator, or if or maybe just humans in like a billion years, there's like or maybe a supercomputer, I don't know, or like an AI in a supercomputer, but some smarter being might just see a bunch of photons bouncing around and to think that all of our notions of space and time are very silly. Like, just how I pointed out how that length contraction effect was just one very weird slice that you take out of an object moving a different reference frame. I think a very smart being might see all of our measurements as just very arbitrary, like blobs that we drew on space-time. Like we draw a bunch of blobs in space-time and say, oh, this is an object. While the smarter being says, no, it's just a bunch of photons bouncing around. And like, you kind of know that, like, and you're kind of ignoring some of the details here, and making some arbitrary choices about like what length and simultaneity are. And it's all just a bunch of ageless, timeless, structureless photons moving around. Okay, cool. Einstein said it in a certain way. Einstein said, it's all just energy, depends how you look at it. Okay. So maybe take it from him. Okay. Questions on matter versus photons? No? Okay, cool. So yeah, so the math part here is what happens if you take the limiting case of this Lorentz boost, the whole system breaks down. But the physics is super strange in that this breaking down, you can't get there, right? It's not physical to get there, but the end part of it does actually exist. There are actually photons that exist. So photons exist and other causality speed things, and objects exist, so to speak. Like we talk about them, but you can't get from one to the other. The mathematics breaks down if you try to get from one to the other, but somehow our objects are constructed of all of these photons flying around. So, and one way of saying it is that objects exist, and if you try to accelerate any of them towards the speed of light, the system breaks down. I prefer the other way of doing it. Like we know these causality speed objects exist, but somehow we manufacture non-causality speed objects to exist, which are little blobs around things and make little clocks. Okay, cool. Great. So that's most of the, oh wait, okay. So I think we talk about rapidity. There are 3 more things I want to talk to you guys about. So okay, one is resolving a paradox from last time. So last time we talked about the twin paradox, where we said you have Earth and you have 2 twins there. One of them flies away from Earth and then turns around and comes back to Earth. And the question is, which one aged more? Because we know that for moving observers, time slows down. Okay, so for the the twin that left Earth, we could say they could say that Earth is flying away from them, and then Earth comes back to them. So if they can both say that they're that they're stationary and the other person is moving, then how can you say which one ages more? The punchline is that the twin that comes back to Earth, so the astronaut twin aged less. But why? Where's the asymmetry? Well, like all so-called paradoxes in special relativity, there's a trick somewhere. None of it's a mathematical paradox, it's just an intuition paradox, which means they had to lie to you at some point. All physical so-called paradoxes feel dumber and dumber as you understand the subject more, because you realize that they're lying to you from the first sentence of the paradox. They try to claim, so the place that they're lying to you first in the twin paradox is they're trying to paint it as a symmetrical picture, but it's clearly not, because one person changing directions means that they exist in 2 different inertial reference frames during their journey, while the other person is in a constant inertial reference frame. And that's the asymmetry. One person experiences 2 reference frames and the other person experiences 1 reference frame. So then you could think of it as, some people like to think of it as the acceleration that the astronaut does is the important part. But even if they accelerate instantaneously somehow, the paradox has the same answer, but it's because one of them is in 2 different reference frames. So if you have 2 people that are only ever each in 1 reference frame, you can just Lorentz boost the whole system back and forth between them. It's completely symmetric, just like with the barn ladder paradox. The farmer and his son were both right or both wrong or whatever. So the both right but both like naive, and just focus on their own perception. But in the twin paradox, there is an asymmetry in that one person is in 2 different reference frames. You can't boost between them because our like locality thing is broken. All of our space-time diagrams depend on being able to extrapolate these local notions to all of space-time, but you can't do that anymore with the twin paradox because one person changes reference frames. Okay, but then I tried to argue to you that if we live in a closed universe, so if space is actually a circle and time is a line, so it's like S1 cross R, it's like a cylindrical universe, the twin paradox has the same resolution. So what do I mean by that? I mean, one astronaut twin leaves Earth, goes really far in that direction, and wraps all the way around and comes back. You could think of a wormhole on both sides of reality that connect of space that connect them, or you could just think of space as like, if you can get your head around it, space is literally a cylinder. So then the twin runs around through space and comes back. Okay, so it turns out the astronaut twin still ages less. And the reason is that, like any good paradox, they lied to you somewhere. This is not symmetric at all. So the reason it's not symmetric is that in a closed universe, your causality grid, your causality lines wrap around the cylinder, whereas a rest frame goes just straight up the cylinder. And you can't boost from, okay, so now if you have if you're moving at any velocity, you are moving with the causality lines. At least a component of your motion is moving with the causality lines. So the causality lines tautologically, like by definition rather, the causality lines by definition in this scheme wrap. A causality line wraps around the cylinder. That means that motion by definition has a component that topologically wraps around the cylinder. So when you frame the paradox, you say one observer stays on Earth and the other observer takes a lap around the cylinder. How do you know that observer took a lap around the cylinder? It's because you know they moved with the component of their velocity in the direction of the causality lines. Like it's all just wrapped into the way you said it. It's a trick. It's a riddle, really. It's like a word trick. Like, so with the barn ladder paradox, it's truly symmetric. Like you just say one thing is moving, the barn is moving relative to the ladder, and then you could switch it around and say the ladder is moving relative to the barn, and that's totally fine. But here, there's an asymmetry baked into the very first sentence. We said that one astronaut took a lap around the cylinder of spacetime, and the other observer did not take a lap around the cylinder, and that's the asymmetry baked into it. If the two astronauts, if the two twins, if one of them didn't, like, there has to be some way that they know that they took a lap. That's built into the whole problem, and the fact that we know that, it's just like, you know, Monty Hall with the it's similar to Monty Hall with the like Monty Hall problem. Like the person telling the story knows something, and that's baked into it. We know that one person took a lap, which means they had to be moving with the components in the direction of the causality lines. So like any good or rather bad paradox, the answer is baked right into the first sentence. So let me just say it as a mathematician. Here's the twin paradox in a closed universe for a mathematician. A mathematician would say, well, you have one observer who does not take a lap through space-time. They topologically do not wrap around our cylindrical universe. Another observer who does take a lap around space-time, wrapping around our cylindrical universe. Which one of them will age more? Well, okay, the one that took a lap had to have been moving to make progress around the universe. So obviously they were the one that was moving, which means time was slowed down for them, which means they aged less. Like you just gave it all away in the problem itself. How would somebody possibly make a lap around space-time and not be moving? It's basically, you just said one of them's moving around a closed universe and came back to where they started while the other person stayed still. Okay, there's one more detail here, and it's that Einstein said that locally reference frames are equivalent. But the thing is that there apparently can be global phenomenon that's not relative. So if you're talking about the entire universe, you can say things that are objective. So like the barn ladder paradox, I don't care where in space it is. They're not traveling a very far distance. They're just hanging out in their one little farm. So they're perfectly fine to go back and forth between their viewpoints. But the reason that the closed universe twin paradox has an asymmetry that we can't just boost away is that we said something very insanely dramatic. We said one of them went around the entirety of the observable universe. Like they went all the way to one end, then came out the other side and came back. The entire observable universe. Boosting is a local phenomenon. And like we said before, these space-time diagrams only work because we don't change directions. But globally, you can have objective things happen. And the reason is that you're comparing it against space-time itself, the whole theater, the whole domain of space-time. Okay. In a very, very mathy sense, Lorentz boosts and relativity and stuff all happens on the tangent space, which is just attached to one point of the manifold. The twin paradox in a closed universe is appealing to the manifold itself. And that's how they try to trick you, is they try to prey on, as an undergraduate physics student, they try to prey on your lack of understanding of manifolds by try to apply a local tangent space notion to the entire manifold. And that's the trick. And it sucks because you can't even explain that to an undergraduate physics major properly. So I really need to go back and ask some of my physics teachers from college how they would explain to a physics student why these paradoxes don't work. So I don't even know if they can give very good answers. They trick them and lie to them so much that it's a deep hole to dig out of. But yeah, okay. For math people, it's not so confusing. Yeah, which is kind of the thesis of this whole thing. Okay.
So question.
Yeah.
So if I understood right, your understanding of the cylindrical version of the twin paradox is that where the trick is baked in is the twin who is traveling has wrapped around the cylinder, whereas the twin who is not traveling is not. Now to make sure I understand right, and maybe to push back a little bit, I guess. Back in like lecture 1 or something, you were talking about the difference between a vector space versus some other kind of space where there's not an objective zero.
Oh, the affine space. Yeah.
Affine? A-P-I-N-E?
A-F-F-I-N-E. Yeah.
Okay. Right. So it seems to me though that understanding of the cylindrical version of the twin paradox does depend on a notion of an objective difference between someone is moving with respect to the world, to the universe, and the other person is still with respect to the universe.
Yeah.
Am I misunderstanding, or is that is there such a thing as an affine space on S cross R?
Right. That's a really good point. So let's work this out. So so I started by arguing, you're right. In the first lecture, I started by arguing we live in an affine space. There's no preferred origin. Everyone can pick their own origin and then pick their own basis vectors for reality, a space and a time, like a causality and a ticking clock. And everyone picks their own. And then we come into conflicts by comparing them and taking our version too seriously, like with the barn ladder paradox. So let's say we have a cylindrical affine space. That's fine. It has no origin. It's just a space. There's a bunch of points. We're in the habit of labeling points with coordinates. Let's just say we label all the points with just like words in different languages or whatever, or just weird symbols or hieroglyphics or something. There's no order. Or coordinates. They're just a bunch of points in a cylinder. It's an affine space. Right. So I think a way of saying that's a really good perspective. I like that question a lot. A way of saying this is that the closed universe twin paradox cheats by trying to apply the principle of defining your own vector space, but without admitting that they've already picked one in the setup of the problem. They've already picked the vector space and set up the problem. So if you know anything about topology, when you have a space and you try to draw a closed curve, you need something called a base point, which is just a point to start at, and then you draw a curve and it ends on that point. They're picking a base point, basically. They're saying someone takes a loop, they take a lap. But how do you define a loop? You start at a point and you go around, you end up back at that point. Like topologically, that's like what a loop is. So if you have a loop, and that means you defined a base point, and if you have a base point, you're in what's a topology way to say this? It's not just a topological space anymore. It's a signed topological space. No, it's a marked topological space. I think that's the way to say it. Yeah. So the topology equivalent of the affine space vector space thing is you go from a topological space to like a marked topological space. That's what they did. Is that in their sentence they said, oh, well, you have a point Earth that you start at and get back to, but that marks the space. So then in linear algebra sense, you've already picked a vector space. You picked a vector space, but now they're saying, oh, well, both twins are free to pick their own vector space and say that they're the stationary thing. But no, they're not, because you already told me that one of them, or you already told me how they're both living after picking a vector space. Any description that you can do in a totally vector space agnostic way will be symmetric, just like with the barn ladder paradox. The barn ladder paradox, we don't say an objective, there's no objective points in space. In a barn ladder paradox, there's a barn and there's a ladder. One's moving, or you could say the other one's moving, whatever. we only ever say one's moving relative to the other. We don't say they're sitting on the ground. We don't say like there's some light post that's like some objective point of reference. There's no points of reference. There's no base point. There's no vector space choice. But the closed universe twin paradox definitely does pick an objective point, which is the Earth, that you have to come back to. So it's lying because it's saying, oh, apply this affine space principle, but we already baked in a vector space. Does that make sense?
Yeah, I think so. So then how would that be affected if we alter the problem a little bit, such as what if the twins were traveling at first and then twin A gets dropped off at the Earth, twin B continues to loop around and then picks up twin A and they continue to loop together? Would this reverse the choice of which one ages?
Right. So I think what you did there is you still baked in a base point, because you said that one looped around, right? How do you know they looped around? Like, so if you just had two twins floating through space and so there's no Earth anymore. The Earth is a trick in the whole thing. So you have two twins and they're floating in space and they fly away from each other and then they come back together. There's definitely no way for either one to say who was actually moving or not. We flew away from each other and then we came back. We definitely were in multiple inertial frames, but the problem's symmetric. But if you say now you have a closed universe and like the two twins, they're chilling and then they fly away from each other, they can't tell which one of them is moving. And then all of a sudden from the other direction, they see the other one coming back again. They'll both see the same thing. That means that one of them took a lap. From their perspective, yeah, they have a hard time figuring out what's going on. But from our perspective, we said one took a lap, which means we're already saying that we already understand the global topology of their world line. I think from their perspective, okay, so then now, okay, let's try to think about it from their perspective. You just have two twins and they're chilling. Okay, you and me are floating in space and we see the other one getting smaller and smaller. They're flying away from us. They're vanishing away in this little distant point. I mean, I guess you would see infinite copies of them in a closed universe, but anyway, maybe like unwrap the cylinder over all of space. But anyway, so then we we look behind us and we see, oh hey, there they come again, and then we come back. It's like, okay, you're back. What happened there? Could we both consider the other person to have taken the whole lap? Could we both have considered the other person to have taken the whole lap?
Or half the lap.
Or half the lap. We both went around and met. If space was completely structureless, yeah, I think that'd be fine. If space was completely structureless, it would have this rotational symmetry to it, and no point around that theta would be special. So, I mean, whether we considered you to have flown away and met me around, or me to have flown away and met you around, or both of us to have gone halfway or some fraction and met at some other point. If space was really, truly structureless, and completely symmetric in this theta, we had no way of knowing who was moving relative to any other objects. Yeah, I think that's totally fine. And we'd age the same. We'd age the same? We'd have to, right? We'd have no way of knowing. Yeah, we'd have no way of knowing. But oh, no, I got it. I totally got it. I think I've got it now. Okay, I've got it. We've got to do Einstein's thing. I hate myself. I'm going back to Einstein. All right. So if we live in a closed universe, that means that light travels along diagonal lines that come back to the same point in space. They wrap around. It's a helix. It's a causality helix now. It's a helical grid that wraps around the cylinder. That's the background now. So then we set up, we could, if we wanted to think about it in boxes, set up an Einstein synchronization within that. So we're inside of causal diamonds, that twisty causal diamonds now, helical diamond things. And within those, we set up a synchronization. Now we have salvaged a notion of space, simultaneous space slices, and ticking clocks of time. And then from there, we can definitely measure who's moving more. If in the general case, we're both moving some, we can measure who's moving more and rationalize to ourselves why one of us aged less than the other. But we can do it even without Einstein's synchronization if we just realize that causality lines wrap around. So the whole perspective of my like PDF here is that you can use this background causality grid to say things about things. And it's really all you can use to say things about things. So in a similar way, we know that causality lines wrap around. So we can use that to say things about things. A causality clock, a really big causality clock, if you really took your time on one of these causal diamond experiments, it would wrap around the entire observable the entire universe as you're doing your little experiments. And using that, it's not a diamond, and it's still a diamond, it's just wrapped. Using that weird diamond, you can say things that are objective. Exactly how would you do that? I'm in a box, you're in a box. In my box, I do an experiment, and right, okay. So we can do like a one-way causal diamond experiment. Instead of waiting for it to bounce off a mirror, I'm just going to send off a light ray in that direction and wait for that same light ray to come back to me from the other side. And I time it. I time how long it takes. Yeah, I time how long it takes. And then I know, so it took a year. So now I know that the circumference of the closed universe is a year divided by the speed of causality, or the speed of light. So now I know the circumference of the whole universe. Now I know the circumference of the whole universe, and I know it's closed and all that. And then as we're, okay, so now how do we figure out which one of us, so let's say one of us, let's posit that only one of us is actually making a loop around the closed universe. Yeah, we can do two different experiments. You can do a local one where you just do our little causal diamond thing. And you can do another experiment where you wait for light rays to come back around. Here's the thing, right? If you are actually going around and around and around the cylinder, those light rays, oh, wow. In a closed universe, there's another unit, and that unit is the circumference of the universe, right? Like that's a new unit. So if you're actually going around the universe, you won't see the light rays that you sent off in one direction take the right amount of time. And that's not breaking Einstein's postulate, because you're not resting on just the speed of light anymore. Now you're comparing the speed of light against something. You're comparing the speed of light against the circumference of the universe. If you really are stationary in a closed universe, then you will always see your little light pulses that you send off in this direction will always come back to you at the same interval. But if you're moving around the closed universe, they don't have to come back to you at the same interval anymore, because it's not just a symmetric case about using a background causality grid, because the light pulses coming back are dependent on the speed of light and on the circumference of the universe. But if you're running around the universe, running away from them, you screw that up. So then to move around a closed universe, there is a measurement that you can make. Your local measurements still have the same problem. My local measurements, there's no way you would know who's moving. Like our causal diamonds would still have the same arguments that we used here. It's all local. But you can make a global measurement now, which is an insane experiment that uses the entire universe. But if I send off light rays in that direction, they come back to me here. If you're moving and I'm not, like if you're making laps and I'm not making laps, we're definitely going to like measure different things there, because mine are a consistent pulse, because I'm basically just measuring the circumference of the universe. But you're going to measure a screwed up circumference of the universe because you're moving through it yourself. It's like trying to measure the circumference of the beltway as you're driving around it, but you're not taking into account your own motion. It's definitely not symmetric anymore. Does that feel right? I think that's right. I think that's the trick. There's a circumference now.
Yeah, sounds okay to me.
Nice. Wow. All right, good work, team. I'm gonna put that in the PDF. All right, cool. So great, we solved that paradox. Let me show you a thing. This is called relativistic beaming. I haven't showed you any two-dimensional effects yet. Here's a two-dimensional effect in special relativity. So there's this crazy thing that happened. I think it's crazy. It's really weird. If you have a light bulb that's flying through space, it's emitting light in all directions, and it's moving at relativistic speeds, or any speed, but it's moving at relativistic speeds. The light rays coming off of it will tend to beam, so to speak. They focus themselves in the direction that it's moving, like a laser. So if you have a light bulb, if you have a star flying through space at 0.9 C, almost all of its lights that's emitting will be beamed in the direction that it's moving, and its wake behind it will be very dull. So the reason for this is it's kind of like chasing causality. So here we have a two dimensions of space and one dimension of time diagram. So here's one dimension of space, here's a second dimension of space, and then vertically is dimension of time. So our causal cone like really does look like a cone now. So these are light rays that go off in every direction in space, and they go off. They have to move through time also, and the slope is still 1. Does the picture make sense right now that this is like one? This is one light pulse emanating through space and time. Each horizontal slice is like a slice of space. So here's like a slice of space. So here's like when the light pulse is emitted, and then here's a circular light pulse at some fraction in time, and then that light pulse like expands out in time. So you have this like ring of light expanding out. Does that make sense? Okay, cool. So what happens if we boost this whole reference frame and this whole light cone thing in some direction? The light cone's got to stay stationary, but all these little reference points here don't have to. These are just points along the like points where we measured the light. So like we measured the light here and here and here, and we see that's expanding uniformly in every direction by like the inverse square law, 1 over r squared. So let's boost this thing. Oh, I lied. The dots are the the dots of the light cone that don't move. This is, oh wait, no, sorry. The light cone is okay. So the light cone is being preserved, but there's a subtlety in that it's not stationary. So the light cone lands on the light cone, but all the points on the light cone don't stay where they used to. The reason this looks like it's missing here is just because I only rendered the light cone out to a certain distance. I think maybe actually I can stretch that out. Whatever. So then what happened is the whole light cone got bunched up towards this direction. I would like to, let me show you that with the points instead. Boost the points. Oops. Oh, I have a button that just takes me to where I want to go. That was nice. It passed me. Ah, sweet. Okay. So okay. So the idea here is so you're gonna imagine a light bulb stationary, and light is just flying away from it in every direction evenly. But now, let's say you're stationary and you see a light bulb flying through space. Well, if it was like dust coming off the light bulb, then the velocity would add and it would all still move together. But it's not. Light still moves at the same speed. So the light bulb is moving at 0.9 c and it's emitting light continuously from it. But the light from it is still only moving at the speed of light. It's kind of chasing the light that's emitting in the same direction it's moving, and it's running away from the light in the opposite direction. And the net effect of this is that you end up doing this transformation that skews all the light in the direction it's moving. It's like this Doppler effect kind of thing. We see that here, that these beams get bunched up over here and they thin out in this direction. Another way of saying this would be, we know that the light bulb, from its perspective, sees light flying away from it in every direction equally because of relativity. But from our perspective, we also have to see the speed of light traveling at the same speed in all directions. So then there's this bias where, from our perspective, the only way to compensate is you need, relative to time, denser packed light rays in the direction it's moving to compensate. I should probably show this in a matrix somewhere in the actual PDF because it's supposed to be about math, so I can explain it rigorously instead of qualitatively. Yeah, so a moving observer, light bulb or not, is always chasing, always seems to us, to a stationary observer, like it's chasing causality. And the way to remedy that in multiple dimensions is you take this transformation that like Doppler shifts causality in their direction. So the analogy is that when you have, so why they call it Doppler shift. So the Doppler effect is when something's moving through air and it creates these, anything that creates sound is ripples of air. So when something's moving through space, moving through air rather, in the direction it's moving, it's emitting these sound waves, but it's catching up to them as it moves. So they get bunched up in the direction it's moving. So the pitch increases because pitch is just about the frequency of the sound waves. The effective frequency goes up. So the weird thing about light is that everyone perceives those waves as moving at the same speed. So the idea is the causal Doppler shift has to undo what the the sound Doppler shift does. So to do that, it has to do like this reverse transformation, and it ends up beaming not just light, but like causality itself in the direction that it's moving, just to counteract this effect. Space, causality is not allowed to bunch up. We're not allowed to see the speed of light being anything other than the speed of light. You can kind of imagine you have an observer, they're moving away, and they're in this sphere. And the transforms are, they're transformations of the Riemann sphere. It's like the Mobius transformations, actually. But it's like just like the set of conformal transformations on the sphere. But it's called like the Minkowski group or something. Or yeah, anyway. So or I think it's called the Lorentz group. It's called the Lorentz group, right? Yeah. So then all of the yeah, so along this sphere, the sphere is preserved, or the cone is preserved, whatever you want. But the lines along the parameterization of it bunches up in the direction that it's moving. So we see this in the real world. We see that things moving are way brighter. The light coming off of them is way brighter in the direction that they're moving. Yes. Yeah, that kind of makes sense. Okay, because here what I did is I literally applied the 2 dimensions of space and 1 dimension of time Lorentz transformation to this system, and we see that the light cone didn't go, or these black lines that are along the light cone, they didn't. Sorry, these black lines are reference points. This is the stationary frame measurement, but these red lines, hold on, how do I explain this the right way? Let me boost the cone and show you that. I like that way of thinking about this. Okay, so we see that the cone stays on the cone, like these lines are still slanted like this, but the parameterization of it bunched up. So that's the trick, is when you have multiple dimensions of space, this Lorentz boost could do something really interesting in that we can exploit our multi-dimensional causality grid. In 1 dimension of space and 1 dimension of time, you have to stay along the causality grid. So the Lorentz boosts always just compress or squeeze, or compress or stretch along the causality grid. But you have 2 dimensions of space and 1 dimension of time, then what you're allowed to do is you have you can like swing along the other dimension of space. The causality grid is like these causality like rings, and you can like swing along the rings. So it's like this, it's this effect that definitely only occurs in multiple dimensions of space. It certainly cannot show relativistic beaming on our flat diagrams, or on one diagrams. But in 2 and 3 dimensions, there's a little loophole to preserving the causality grid, and it's that you can swing into the other spatial dimensions. So your direction through space and time will squish in every direction of space towards the direction you're moving, along causality circles or causality spheres, actually. Yeah. Does that qualitatively make sense? I'll try to put some pictures in the PDF. Okay, cool. So yeah, like I mentioned before, I'm far too far to give up on this now. So this will definitely be finished, and I'm really trying to get it done by the end of the semester because I have other things to do in the summer. But there's one note at the end of I already wrote the end of the manifesto, so I'll just tell you the last thing I wrote here. So the thing I started with was a quote by Descartes. You know, imagination is best left to mathematics and best left out of the metaphysical sciences. It just gives us all these fanciful things that confuse us, like length contraction and time slows down and stuff like that. Non-physical things that trick us. So keep the imagination out of physics. Try to take it literally. Try to take it mathematically. So dual to that, a healthy dose of analytical nihilism at the end here to really put a nail into fanciful thinking in physics. So you might have heard of Gödel's incompleteness theorem before. Gödel's incompleteness theorem is a statement that any formal system will have, so any formal systems that could be first order logic, could be language, be calculus, it could be like all of philosophy in some abstract way, arithmetic, computation, classical or quantum, any formal system in a logical sense. So it has to, that formal system has to have a certain expressive power. In particular, it has to be able to do like addition and stuff like that. It has to be like Turing complete. But it's not hard to make that happen, actually. Microsoft PowerPoint is Turing complete. Okay. Anyway, Minecraft is Turing complete. Okay. So any formal system will have statements that cannot be deduced to be true or false. So in math, we do proofs of things. But the thing is, if you set up a formal system where you want to say things, we've proven logically that any system like that will have statements that you can never deduce a true or false assignment to. So if you, right, and then, I'm sorry, and also no formal system can prove that it's consistent. Consistent for mathematical logic means that all of the statements don't contradict, all the true statements that can be proved don't contradict each other. There's no contradictions that can be derived. So no matter what formal system I give you, Gödel, this guy Kurt Gödel, he proved that you can never use that system to prove that that system is A, infallible, and B, answer every question. And what this does is it destroys the idea of a theory of everything. The theory of everything is a physical theory that you can write down in a finite amount of space that describes all of reality. But the thing is, that theory of everything that you write down, even if it's a whole book of equations, it's a formal system, which means there's always going to be statements you can write down that you literally, mathematically cannot prove true or false, which corresponds to a physical phenomena that you can't explain with the physical theory. There's always going to be a paradox, a thought experiment that someone can come up with that your physical theory won't have the answer to. And if you add the answer into your formal system as a new axiom or a new law of physics or a new force of nature or whatever, it just pushes the question back to Kurt. And then, you know, Kurt's like, yeah, sorry, that's just a formal system. And you can't say anything about it. So I started this off by trying to point out that physicists are tricking themselves by thinking they're doing physics. They're actually just doing math. And when you look at it as math, you these paradoxes vanish because you kind of humble yourself. You realize you're just doing math. And then the ultimate nail in the coffin of physics, the thing that Einstein literally died over trying to come up with the theory of everything, is that you can't actually do it because physics doesn't exist. It's just humans doing math, trying to describe our observations, which are also just mathematical objects. It's all up in Plato's form, Platonic forms. It's all just math. It's desperate grasps at trying to conquer reality, but we can't actually ever do it. There's physical reasons why we can't ever observe everything, but more fundamentally, there's mathematical reasons why we can't describe everything. And this is why I think that physics is more a reflection of ourselves than it is of the physical universe. At the end of the day, we're a bunch of conscious beings that are sitting around creating these cool structures that we call math and comparing that against each other and comparing them against our own intuition and measurements that we make, which are just other mathematical constructs, and trying to investigate the depths of our own minds. I think the ultimate form of physics is that it's going to give up on trying to conquer all of reality in a very imperialistic way, like trying to understand everything, every morsel of reality. And we'll realize that we need to like turn inwards and reflect on, you know, what we're doing by studying the metaphysical universe is really just probing the mathematical possibilities of our own brains. What kind of constructs can you come up with and what can we do with them? Physics doesn't exist, it's all just math. And that's the end of my seminar. Thanks for coming.
Well, before we wrap up, I wanted to take a minute on behalf of our NYU SIAM e-board to just really sincerely thank Ajeet for you know, all of his hard work to prepare these 6 seminars, and now I'm finding out pages and pages and pages of notes. We are so grateful and so impressed, you know, with this sort of forum that you've created for undergraduates, and we know that, you know, it's really not a typical undergraduate experience. So we're just, you know, we're really grateful, and you know, we hope you know that. Let's all give Ajeet a round of applause, please.
Yeah, thank you all so much for coming. You guys being here, even if it was just listening sometimes, separated this from some weird rant in my notes to something productive, that you held me accountable, that I had to make some sort of sense. So thanks for coming. And I owe you the rest of these notes, which I will create. And that virtual reality thing, once I get it done, I'll post also. Oh, and the link to my GitHub is on this same site and in the chat, because Google Sites wouldn't let me post the Mathematica code, but the Mathematica code is on my GitHub now. So all the models that are in this paper, the models are in the Mathematica notebook and the ways I generated them. So any space-time diagram that you want to create, or causality boxes or anything like that, the tools are all in that notebook, and I think explained pretty well. Yeah, and if you ever want to talk special relativity or physics, shoot me an email. So yeah, thanks for coming, and have a good rest of your semester.
Ajeet, have a good one.
Cool. See you.
Thank you.
Thank you.